Hello everybody, I'm Sorry Zhang from University of Houston and I'm going to present our work Recursion brings Speedup to after-core TensorCore-based linear algebra algorithms. In our work, we select the classic Gram-Schmidt QR factorization as an example to illustrate our recursive strategy. At the very beginning, let me introduce the TensorCore a little bit. TensorCore was introduced by NVIDIA in 2017. TensorCore supports half-precision computations with very high speed. Typically, half-precision has two standards. One is P16 and another is bflow16. Both of them have 16 bits. The differences are the range and the unit round of error. P16 has smaller range with better accuracy and vice versa. The usage of TensorCore is restricted in matrix multiplications because it only supports 4x4 gems. The advantage of using TensorCore is that it's extremely fast, and the performance comparison is shown here. After introducing the TensorCore, let me give another brief introduction to the after-core processing and QR factorization to make it easier to understand our work. QR factorization is a matrix factorization that decomposes a matrix to a product of the orthogonal matrix and the half-triangular matrix. There are typically three algorithms that can do this work, including Gram-Schmidt, householder, and Gibbons rotation. In our work, we select the classic Gram-Schmidt as an example. The steps of the classic Gram-Schmidt are shown here. In short, it finds the orthogonal basis one by one. The project A is an orthogonal projection of the vector onto a unit vector. We can also obtain R during these steps. To make the QR factorization run fast on modern architectures, the blocking technology is introduced. There are two types of blocking strategy. The first one is a conventional blocking algorithm. See the figure on the left. We first perform the QR factorization on the panel and get Q1 and R1. Then we use Q1 and R1 to update the A2 and compute R12. Repeat their steps until that panel is factorized. Recursive strategy is shown in the figure on the right. We divide the matrix into two half submatrices until the submatrix is small enough, and we also call the submatrix panel. Then we perform QR factorization on the left half panel and then update the right half panel. Finally, we can factorize the whole matrix recursively. The out-of-core processing is usually used when the memory is limited. For example, if we want to perform gem with size 1 million by 1 million on a single processor, then we will need at least 12 TB memory. It's very hard to execute the entire gem at one time. Thus, we can store that on disk and read it and multiply them block by block. This is called out-of-core processing. Similarly, we can also do it on GPU because the GPU memory is typically less than the CPU main memory. There exist several out-of-core applications such as Solar, ScalaPark, XT, and BlastX. Now the problem is how to combine the three things together. Suppose we have a big matrix that cannot be fit into GPU memory, and we also want to use TensorCore to factorize the matrix. It's very easy to come up with some ideas that follow the blocking or recursive strategy. For example, we can factorize the first panel on GPU and then update the rest of the matrix using out-of-core gems. But why don't we use the recursive strategy? Is there any difference between them? In the next section, I'll give some performance analysis to show why the recursive strategy is better when we are using TensorCore. The first thing we are caring about is data movement because lots of time will be spent when we are doing out-of-core computations. We did a simple calculation of the data movement from device to host and host device. Here are the results. The M is the number of rows and N is the number of columns. The B is the block size and the K is the number of blocks, and it can be obtained from N divided by B. We can find that the amount of data movement in the blocking algorithm is linearly related to the K, while the amount of data movement in the recursive algorithm is linearly related to the log K. This means the larger matrix is, larger gap between the blocking and the recursive algorithm. We also did an experiment on this. The table shows the overall time consumption when doing out-of-core QR on GPU. We can find that the blocking algorithm spends more time on moving the data. The second thing is the overlap ratio. We know that the recent GPU support concurrent computations when moving data. This means if the time cost of the computations is larger than the time cost of the moving data, then the entire computation will be computing dominated, and this is what we want. To make the problem simpler, we will analyze the inside of the core gems at first. We have two types of gem. The first one is updating the OR matrix termed as inner product. The second one is updating the rest of the matrix termed as out product. A blocking scheme is slightly different between the recursion and blocking to ensure most of the data can be reused. In the recursive gems, we divide both A and B into several blocks and let C store on the device. While in the blocking algorithm, we let A store on device and divide B and C into blocks. Assume the GPU tensor core rate is 19 teraflops and the data movement rate is 12 GB per second, and we want the time cost of gem is larger than the time cost of the moving data. Then we have the number of rows to be larger than 30,000 in the recursive gems, while the number of rows should be larger than the 15,000 in the blocking algorithm. It seems that the blocking algorithm is smaller, but one thing should be mentioned that the block size of the blocking algorithm is fixed and typically less than 15,000, while the M in the recursive algorithm is not fixed. At least the largest gem can enjoy the entire overlapping. Similarly, we have the blocking strategy of outer product. For the recursive algorithm, we let B store on GPU and move the blocks of A and C from host device. For the blocking algorithm, we move the blocks of A, B, C forward and backward. Still, we assume in the in-core gem and the data movement rate to be the same. Even though the equation is different, we can still find the result is the same, which means the overlap ratio of the recursive algorithm is higher. This table shows the experimental results of the biggest of the core gems in the recursive algorithm and the blocking algorithm. In terms of the inner product, the in-core gem in the recursive algorithm is much faster than the gem in the blocking algorithm. This is because of the shapes in the recursive algorithm are better than the shapes in the blocking. So it's not surprising to see the final asynchronous rate is around 2 times faster. And this figure shows the timeline of the computing gems. We can find that both of them can overlap the data movement, but the recursive gem has a better performance on the in-core gems. When it comes to the out product, things become different. See this table, we cannot find a large difference of the performance. Both of them can overlap the data movement, and the in-core gem rate is very close. But when we limit the GPU memory to be 16 GB rather than 32 GB on V100, the gems in the out product cannot overlap the data movement anymore. See the second timeline figure. The overall time cost is larger. At the same time, it can also see a big difference in the recursive algorithm when the block size becomes 8,000. Note that on the most widely used GPUs such as RTX 20 and 30 series, the GPU memory is typically less than 16 GB. The implementation and optimization are quite simple if you use CUDA streams. Another trick can be used is gradually increasing the block size to the right overlap ratio in the first block. Actually, we can get around 2 teraflops increment when we are using this trick. The QR level optimization means the interaction between the panel factorization and gems. We need to cut off unnecessary data movement and use different streams to overlap the data movement. For example, when we are factorizing the first panel, we can let the panel stay on GPU and join the following gems. The final results are shown here. The slide shows the timeline when the GPU memory is 32 GB and the block size is 16,000. We can find the recursive strategy is slightly faster than the blocking strategy. In this case, the speedup is from the in-core gems in the inner product. When the GPU memory is limited and the block size is reduced to 8,000, then time cost increases significantly. The timeline is shown here, and in this case, the speedup is mainly from the overlapping. We have also done some proof experiments with different shapes and sizes, and the results are shown in the table. It's obvious that even with non-square shapes and smaller sizes, the recursive algorithm still has better performance. So, what's our conclusion? Surely, the first one is that the recursive strategy can bring speedup to the after-core QR factorization because of 3 reasons. First, it has less data movement. Second, it has higher in-core gems computation rate. Third, It has large overlap ratio, especially when the memory is limited. The second conclusion is somehow hard to find out. When we are reducing GPU memory or training V100 to RTX 2030 series and keep the computation rate at the same level, we can observe a big speedup of a recursive strategy compared to the blocking. The same, when we are increasing the computation capacity while keeping the memory at the same level, such as changing V100 to A100 GPU, we can also get a bit speedup. Because for the blocking algorithm, the block size needs to be larger than 60,000, but it's impossible to be implemented because its memory is very limited. But for the recursive algorithm, it's not a big problem because none of the rules is not fixed. It's also interesting to think about not using TensorCore. Actually, if you are not using TensorCore, the GM can always overlap the data movement, so the recursive strategy doesn't have any advantage. This suggests that the higher computation speed and the memory capacity radio is, the more speedup brings by recursion. There are still some other work can be done in the future. The first one is trying to deploy this kind of algorithm on A100 and to see if it can really bring larger speedup. The second one is that the LU and Cholesky factorization is similar to the QR factorization. All of them has a panel factorization in the gems, so it's very possible to see the same results on LU and Cholesky factorization when using recursive strategy. Thanks for your watching.